next we will discuss on thermal hour testing. So, power hour testing, so that was targeted to reduce the power consumption during test. Now, this power reduction is good because the circuit may have some power budget, so we should not exceed that power budget. So, if we exceed that peak power consumption, then circuit may get damaged, and it may also, if the average power is more, then the battery life will be poor. So, those were the concerns. Now, this power alone may not be sufficient for ensuring the goodness of the testing strategy. We also need to consider the heat that is generated in the testing process. So, if a circuit consumes lot of power, so it is expected that the heat generated will also be high, because a good amount of consumed power is dissipated as heat. So, temperature of the chip will be high, and if the temperature goes up, then there are several problems that can come. So, as a result, we need to do something so that this temperature of the chip can be kept under control. And what happens is that most of the chips that we have in today, they have got a dynamic thermal management policy, or known as DTM. So, if the temperature exceeds certain frequency, certain value, certain threshold value, then the DTM policy, so it will try to shut down the chip, or it will try to reduce the frequency of operation of the chip. So, during testing, since the power consumption is high, so it is possible that we cross that the temperature threshold, and if we cross the temperature threshold, the DTM policy will come into operation, and it will put the circuit in shutdown mode, or it will take it to a lower frequency, so affecting the efficiency of the testing process. So, that is why we need to address this thermal issues explicitly in the testing. Now, why this thermal hour testing is so important? Suppose we have got a circuit, and we see that the power profile of the circuit is like this. So, it is divided into blocks. So, if the blocks which are that are cool, so they are deep blue colored, and as we are going to hotter and hotter block, the blocks that are consuming more and more power, so they are turned towards red and towards brown. Okay. So, this we see that among these blocks, so this block A is consume lot of power. Okay. So, that way it is its power consumption is high. So, we will try to reduce the power. On the other hand, if we look into the temperature profile, we may find that block A is not that much a concern, but block C is more of a concern, and the and this block is also a concern. So, which was previously the block C and this one, so they were not of much concern, but when we see the temperature profile, C is more heated than A, and this particular block left side of A, so that is also more heated than A. Why this thing happen? Because the heat that is generated, it has to that is the heat generated depends not only on the power consumption of a single block, but it also depends on the surrounding blocks, because surrounding blocks through this boundary, the heat will be transferred. Okay. So, they will be transported from C to A or A to C, and similarly this thing. Now, if a block is surrounded by some hotter blocks, then naturally it is expected that it will not be able to remove its heat easily. As a result, its temperature will be higher than the block that is surrounded by blocks whose temperatures are not that high. So, that way it will be able to transfer a good amount of its heat to its neighbors, and as a result this will be that will not be that block will not be that much heated. So, this is what we are looking for. So, this power profile, so we can a power reduction technique or a peak power reduction technique will try to reduce the activity in the circuit, so that this block A does not see much of activities. Okay. But a thermal hour strategy should try to reduce the activities for C, so that this temperature of C is not that much affected. So, you see what is happening is that this temperature is dependent not only on the power consumption of the block, but it also depends on the layout of the chip. So, the distribution of temperature is dependent on the layout of the chip. So, there is a spatial information that is also coming into picture apart from the power profile. So, that makes this temperature handling problem more difficult compared to this power handling problem. So, and if we do not handle this, then what is going to happen? So, power this as the temperature of our circuit in our system increases. So, for every 10 degree centigrade rise in temperature, leakage power almost doubles itself. So, if it doubles itself, then it will cause further power consumption and further heat generation. So, that way that may finally lead to a runaway, thermal runaway may occur. So, destroying the chip. So, that way we need to take care of that. Also, another thing is that if different parts of the chip they are differently heated, so their temperatures are not uniform, then the delays of different blocks will also not be same. So, the delay of this block C and say this block or this block, so they are not same because the temperature may have a wide variation, and if it is so, then this delay test will fail. So, delay test in some cases for good circuits it may find it as failure, and for bad circuits it may find it as a pass. So, that way it is also to be taken care of. So, how do we get this temperature profile? So, that is the first thing. So, what is done is that there are many thermal estimators that are available. So, like the one of them is this tool hotspot. So, this is available in this particular site. So, this hotspot what it does is that it takes the floor plan of the chip as an input, and it also takes the power trace of this individual blocks. Okay. So, and then it may be a block level estimator or it may be a gate level estimator. So, whatever it is, so this this floor plan and this power trace, so they are fed to this thermal estimator. It does some thermal simulation. Okay. So, and then it comes up with the thermal modeling. So, it gives the temperature distribution of various blocks in the circuit. So, we will not go into how these thermal simulators are designed and all that. So, that is a part of this thermal estimation process. So, we will not go into that. So, we will be using these thermal estimators to see the temperature profile of the chip, and we will try to see how we will try to see look into the techniques by which this this temperature distribution can be made more uniform, and this the peak temperature of the system can be reduced. So, how can we do this block level simulation? So, it is like this. So, start with the circuit description, then the circuit description is passed through some synthesis tool. So, maybe we can use some tool like Design Vision from Synopsys or some other tool by which we can do the synthesis of the system. So, by this synthesis, after the synthesis we do scan chain insertion using some DFT compiler. Okay. So, these scan chains are inserted into the circuit. Then after this we have got with us the net list with scan chains. So, we have got the net list with scan chain in our hand. Now, we were using some floor plan generation tool can be used. A typical example is the cadence encounter tool, by which we can generate the floor plan corresponding to this net list with scan chain. The net list will generate the floor plan, and then for this thermal estimation purpose, so we divide the floor plan into number of blocks, because this thermal simulator. So, if you make it to work at the granularity of individual gates, then it will take huge amount of time. So, to reduce the time requirement, what is done most of the research works. So, they divide the floor plan into number of blocks. So, that then it does a block level simulation. So, we get, so after doing this blocking, so we get a block level floor plan. On the other hand, these test patterns have been generated by some ATPG tool for the circuit. So, this net list with scan chain, so that is fed with these test patterns to a gate level power estimator. So, gate level power estimator, it will find out transitions occurring at individual gates in the circuit, and that way depending upon the gate type we can have some estimation of the power consumed by individual gates. So, we get the as an output of this gate level power estimator, we can get the power consumption of gates and flip flops, and then we have already divided the floor plan into blocks. So, we can sum the power consumption of individual gates and flip flops belonging to a block and sum them up and get the block level power estimation. So, for individual blocks that we have in our floor plan, so we can get what is the power consumption. Now, we have got these two tools, the block level floor plan is available and block level power estimator is available. So, that they can be fed to some thermal estimator tool such as hotspot, and then it can give us the temperature profile. So, this is the typically the flow that has to be followed if we are trying to get the temperature profile for a circuit and a given test pattern set. So, you see that the process is quite complex compared to say this power level, this power optimization, this low power testing and all that. So, the steps are much more complex, and in particular this at the lowest level to get the temperature values we have to go for a thermal estimation, so which is time consuming, and there is no such straightforward guideline like the scan chain transitions being more, temperature will be more. There is no such guideline like this. So, scan chain transitions being more, the circuit power will be more, but how these individual blocks within a circuit they will consume power, their consumption pattern will change. So, it is not depicted by the scan chains. So, naturally the procedures that we have to use, they are to be more elaborate and more exhaustive in nature. So, we will go back to the we will classify this whole presentation again into two parts that we were looking previously. First part is the external testing, where the test patterns are stored in some automatic test equipment, and from the automatic test equipment the test patterns are transported to the circuit and there it is applied. Okay. So, a very basic strategy that can be followed is the test vector reordering. So, we have seen that the test vector reordering, it can reduce the test power. So, similarly this test vector reordering can also reduce the temperature. So, we will see some techniques, some techniques based on Hamming distance and another technique based on a more detailed approach which is known as particle swarm optimization. So, if we look back, there are some algorithms that have been reported in the literature, which is way back in 2006, Picasso, that tries to minimize the peak temperature to some extent by overheat compensation. So, what this work does is that it takes it classifies the patterns into some pattern which are consuming high, which are resulting in high temperature, some of them resulting in low temperature. So, between these high temperature consuming transition patterns, so they insert this low temperature transition computing pattern, but the problem is that temperature is not a very instantaneous phenomena. So, it occurs over a sequence of patterns. Okay. So, it is not very easy to identify or declare that a particular test pattern is going to consume lot of heat. Okay. It is going to generate lot of heat. So, it is difficult to tell that way. So, they actually try to concentrate on minimizing circuit transitions rather than peak temperature of the circuit. So, naturally they cannot reduce this temperature directly. So, they try to reduce this circuit transition, and average temperature of the circuit may increase. So, what we do is that we compute this in the Hamming distance based approach. So, we will be finding out the primary inputs in cone of dependency and the weighted part of it. So, what happens is that if this is my circuit and after for a given test pattern set T, we may find that this is the block which is becoming very hot. Okay. So, what we do, we figure out the cone of influence, the primary input cone on which this part depends. Suppose this is the primary input cone onto which this block depends. Now, naturally if we can reduce transitions that are occurring in this block, okay, so between two successive patterns T1 and T2 that we are applying to the circuit, if we find that for this part of input the transitions are less. Okay. So, instead of applying T1 T2, so if I apply T1 T3, if we find that in this case transitions in this part is less compared to T1 T2, then it is expected that if I apply T1 T3 instead of T1 T2 in that sequence, then the block that we have in our question, so that will consume less power and it will try it may become its activity will reduce. So, the power consumption will reduce, and that is expected to reduce the temperature. So, that is the Hamming distance based approach. So, we look into the Hamming distance between two successive patterns. So, that Hamming distance being less means less activity. And then there are this particle swarm optimization. So, the work that is reported. So, it will be doing two different things. It will first of all it will use this it will use some sort of metric to model this thermal behavior of the circuit, and the next one. So, it will directly integrate the thermal simulator into the circuit. So, naturally the results will be best when we have got this thermal simulator integrated into the optimization process, but the computation time will be more. Okay. So, that may not be feasible in many cases. So, for on the other hand, this thermal metric based PSO, some metric will be utilized that will reduce the, that is expected to reduce the temperature. So, the cone of dependency, as we were telling, that if this is block 1, then the cone of dependency has got inputs A, B and C. Similarly, if this is say block 2, so cone of influence is the pattern is are the inputs D, E and F. So, Hamming distance based approach. So, what is done is that suppose we have got these three patterns T1, T2 and T3. So, we see that between these two, so this T1, so this bit changes, again here this bit changes. So, these are the bits which are going to be affected. So, this may be for some block, maybe these are the inputs that are effective for this block, the inputs that are marked in red, that may be in the cone of influence of the particular block, and I need to compute what is the Hamming distance if we apply these patterns in this sequence T1, T2, T3 or T1, T3, T2 like that. Okay. So, what we do, we find out, we assign some weight to every block. What is it? This is equal to temperature of the block Bi, which is given by T Bi, divided by maximum temperature of any block T max. So, given a test pattern set which is unordered, so we do a thermal simulation and find out what are the what is the temperature of individual block, and what for the entire chip what is the maximum temperature. So, out of that, so how critical is that block's temperature? So, that is the weight of the block. So, that is computed as this temperature of the block divided by the maximum temperature value. So, this way we get the weight. Now, this cost function is computed as summation of weight of the block multiplied by Hamming distance at the primary inputs in the cone of dependency of block Bi. So, for every block, so these values are these Hamming distances are computed, and it is multiplied by the corresponding importance of the block, that is the weight factor WBi, and that is summed up. So, that will tell us like what will happen if I choose a particular ordering. But the problem that we have in this case is that it may lead to an increase in the transition at primary inputs other than in the cone of the hottest block. So, for basically since we are having this the weight factor which is guided, which is actually depicting which is actually helping the high temperature blocks to reduce temperature. So, in effect it can increase the transition at the primary inputs which are not feeding the hottest cone, but some other cone, and as a result that new cone become now hotter than this one. So, as a result this for other blocks it may increase the temperature, and average temperature of the chip may increase, because we are targeting to reduce the peak temperature. So, the average temperature of the system may increase. So, the mean temperature will increase. So, that may have some adverse effect on the delay and frequency of the chip. Next, we will look into a particle swarm optimization based strategy. So, particle swarm optimization, it is again a meta search technique similar to the genetic algorithm we have discussed some classes back while in the ATPG algorithm. So, it is similar to that, but it is much more I should say efficient in most of the optimization problem. It shows much better result compared to genetic algorithm. So, it was developed by Eberhardt and Kennedy in 1995. It is inspired by the social behavior of bird flocking or fish schooling. So, if you look into a group of birds flying on the sky, you will find that they follow some sort of V type of pattern. So, maybe there is a bird at the top, at the beginning, then there are some other birds which are following that bird. So, they often fly like this, and if you look at it, then we may find that after some time one of these birds they diverges like this, and all of them they start following this new direction. So, apparently this is due to maybe their wish or their joy, but these two people they thought that okay, it may be due to some other reason. Okay. So, they say that these birds they are flying on the sky to search for some food, and they have some estimation of food, and they try to figure out the food where the food is. So, in PSO, particle swarm optimization, that is inspired by this operation. So, every potential solution that is called a particle, it flies through the problem space by following some current optimum particle. So, it is actually every particle is a solution, like in genetic algorithm every chromosome was a solution. Here every particle is a solution, and these particles they fly through the search space. They fly through the search space and looking for some better solution. Okay. So, it has PSO has been applied successfully in many areas, and it has been found that it outperforms genetic algorithm in terms of cost function and execution time in many cases. Of course, there are many other optimization techniques, but we will discuss about it. So, let us see how this PSO is formulated. Okay. So, consider this scenario: a group of birds are randomly searching for food in an area, and there is only one piece of food in the area being searched. Okay. So, there is only one piece of food, and none of the birds knows exactly where the food is. Okay. So, similarly, when we are looking for say solutions, so we do not know the exact optimum solution for the problem. So, we may have some idea about what may be the optimum solution looking like, or where it may be found, but we do not know the exact solution. So, none of the birds knows exactly where the food is, and during each iteration they learn via intercommunications how far the food is. So, every bird has got some idea about how far am I from the food. So, as it is assumed that they have got a strong notion, they can get a very they have got very strong idea like how far am I from the food. Now, birds are thought to be cooperative. So, the bird which has got the best idea, so it tells other birds that okay, see, this is the current best estimation, and all other birds, so they compare their estimate with that estimate, and accordingly take some decision to fly. So, the best strategy to find the food is to follow the bird which is nearest to the food. However, there may be the case that a bird has got its own intelligence also. So, it is flying for quite some time. So, during that time also it has got some idea about where the food was. Okay. So, that way it is guided by two factors. One is the information from the best information about the current best, then a history that the bird has seen during its fly through the space, and some inertia. Okay. So, it was flying in some direction, so it cannot change immediately. So, it has some inertia. So, they will be guiding the flying direction of a bird, or the in our case the change in the solution. Okay. So, that will be guided by this thing. So, PSO is actually learned from this bird flocking scenario, and it is used in solving many optimization problems. So, each single solution or particle is perceived as a bird in the search space. Okay. Each particle, it will have a fitness value which is evaluated by the fitness function, the cost function to be optimized, and a velocity which directs its flight. So, there is a fitness, every particle has got a fitness and a velocity. So, if it is an n dimensional space, then for each dimension it has got a velocity. Okay. So, that has to be that will be updated at every step, and for each direction the velocity will be determined. The particles, they fly through the problem space by following the current optimum particles that is there, and initialized with a group of random particles, that is random solutions, and then searches for optima by updating through generation. So, now rest of the thing is similar to genetic algorithm. So, here also we have got some initial population which may be randomly generated or may be guided by some other heuristic, and then it evolves through generation by considering the global intelligence and the local intelligence. So, during every generation the particle is updated by the following two best values. One is the p best, that is the position vector of the best solution this particle has achieved so far. Since it is flying for quite some time, or the particle is evolving over a number of generations. So, it over the generation, so it has some idea, it has got the idea like when it saw the best solution. And since if we are looking for a say minimization problem, then when the solution was at minimum for a particular particle, or if we are looking for a maximization problem, then when was the solution the fitness value was maximum for the particular for that particular particle. So, that way we have got this this notion about this p best, the position vector of the best solution this particle has achieved so far, and this fitness value is also stored along with the particle. And then we have got g best, which is the global best position that is obtained so far by any particle in the population. So, that is actually the global intelligence. So, this local intelligence and this global intelligence, they are coming and they will be combined to determine the velocity of the particle in the near future. So, we will continue in the next class.